Look up at a high-voltage power line, the primary infrastructure for energy delivery. Every day, hundreds of megawatts flow right above our heads. Moving that volume of electricity over long distances creates a specific engineering problem. You have to push current from a power plant to a city. Alone, copper wins, but it's dense and expensive. Stringing solid copper across hundreds of miles is impossible. Instead, we use aluminum. It provides a 70% weight reduction and significant cost savings. Shedding that physical load introduces a core challenge in overhead design, finding the point where high electrical capacity meets the necessary structural limits. Pure aluminum has a specific vulnerability, very low tensile strength. It stretches and breaks easily when subjected to high physical tension. Think of it like a gold chain. While the material is highly valuable and functional, it will pull apart if you apply too much force. Utility companies must account for high winds, ice accumulation, and heavy environmental stress. Using a weak line means constant repairs and potential failures during storms. To solve this, the industry developed a zoo of specialized conductors. These cables are engineered to combine aluminum's conductivity with various structural reinforcements. There is no single perfect wire. Every choice is a strategic compromise between the muscle needed to survive the elements and the veins needed to carry the current. To see how those compromises work, we need to look inside the wires. High-voltage lines are almost never built as a single solid rod of metal. Instead, engineers use stranding, the process of twisting multiple thin wires together to form a single, unified cable. Looking at this 3D cross-section, stranding offers three distinct advantages. It makes the cable flexible, it reduces the electrical skin effect, and it prevents the wires from snapping due to wind vibrations. The most basic type is the all-aluminum conductor, or AAC. It is made entirely from refined aluminum strands. AAC provides high local conductivity at a low price point. If you are designing for short distances or urban distribution where spans are tight, this is the standard choice. However, because it lacks reinforcement, AAC cannot handle the tension of long distances. For those, engineers have to look towards stronger alternatives. If you're building a line in a coastal area, standard aluminum will fail quickly. That's where the all-aluminum alloy conductor, or AAC, comes in. By mixing aluminum with magnesium and silicon, you get much higher resistance to salt air. You trade away a higher upfront material cost for a line that won't corrode in a sea breeze. When the priority shifts to moving power across a continent, we use the industry standard for high-voltage transmission, aluminum conductor steel reinforced, or ACSR. Take a look at the ACSR row on this scorecard. It solves the strength problem by wrapping high-purity aluminum around a core of galvanized steel. The steel provides the mechanical strength, while the aluminum carries the electricity. ACSR has the tensile strength required to bridge kilometers of open ground. It is the primary choice for the high-voltage spans that form the backbone of the grid. Supporting that much weight requires industrial-scale infrastructure. You need these towering lattice structures to manage the load over long, flat distances. There is also ACAR, which uses an aluminum alloy core. It's a middle ground option for when you need to balance weight with a specific load capacity. Choosing the reinforcement material dictates the entire structural plan of the grid. The wire you pick determines how heavy your towers need to be. In the field, we don't just talk about thick or thin wires. We use precise square millimeters and specific industry code names. We also use a numerical notation called the rule of stranding to identify a cable's exact composition. This cross-section shows a 30/7 layout. That means there are 30 outer strands of aluminum wrapping around an inner core of 7 steel strands. On the right, you can see how sizes range from squirrel to zebra. These code names correspond to ampacity, the maximum electrical flow a line can handle before it overheats. If you exceed this limit, the cable can sag dangerously or lose its structural integrity. As we move from rabbit to panther, the capacity nearly triples. The trade-off is physical. Increasing the cross-sectional area gives you more amps, but it also increases the weight and the mechanical load on the poles. Environment changes these limits too. In high ambient heat, the capacity drops, but a steady wind acts as a coolant, actually increasing the amount of current the line can safely carry. Sizing a conductor is a calculation that has to survive the intersection of electrical load, mechanical weight, and local weather patterns. Let's apply this. Imagine you are designing a line for a factory that needs a steady 200 amps of current. First, we apply a 20% safety factor. That pushes our design requirement up to 240 amps. This flowchart filters the options. We branch off based on environment and span distance. For our inland factory, we need a long span, requiring a steel core and a 240 amp capacity. This leads to DOG ACSR at 100 square millimeters, providing necessary strength without overheating. Using a systematic approach ensures the grid is reliable. It prevents procurement managers from overspending on premium alloys or undersizing critical infrastructure. Each conductor has a definitive role: AAC for local distribution, AAAC for coastal resistance, and ACSR for heavy-duty, long-distance grids. Understanding power transmission is fundamentally about balancing the strength of steel with the conductivity of aluminum. When you look up at neighborhood infrastructure, you are seeing those mathematical compromises in person. Effective infrastructure design matches a material's specific properties to the unique constraints of the environment. Mastering the anatomy of power allows us to build a grid that is both electrically efficient and structurally resilient for the